Waterfall. You see me from a certain point of view. La da 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 da. Oh, oh, oh. Left eye waterfall. Always in my arms, my window. You feel me right. You feel me right, right. Oh, let it wash over me. Man, I wish you were here. That would be nice. If we were if we were studying together here in the lounge on campus. That's so much fun. You see me from a third point of view. Oasis in my arms, my wonder why. You fit me right. You fit me right. I don't need a star. Your face is like a full blown universe. I'm always gonna die where you are. You fit me right. You fit me right. I lay your grace on me. Hallelujah, you amazing. When she walks away, that's my baby. That's my baby. Treat your body. That's my baby. That's my baby. That's my baby. Treat your body like a tree. Eat your body like a river and oh, see you coming at me like a wave. Touch me to a waist. Stars on the lake look like a million diamonds. Let it wash all over me. Treat your body like a river and see you coming at me like a wave. Touch me 10 ways. Stars on the lake look like a million diamonds. Let it wash all over me. Like waterfall. You see me from a third point of oasis in my arms, my wonder why. You fit me right. You fit me right. I don't need a star. Your face is like a full universe. I'm always gonna die where you go. You fit me right. You fit me right. I lay your grace on me. Hallelujah, you amaze me. When she walks away, that's my baby. Treat your body. See you coming at me like a wave. Touch me to a waist, stars on the lake look like a million diamonds. See you coming at me like, oh, yeah. Touch me to a waist, stars on the lake look like a million diamonds. Let it wash all over me. Hey ya, hey ya, hey. Oh, hey ya, oh, let it wash all over me. Hey, do, do do do, do do do, do 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 do. Hey ya, oh, let it wash all over me. Thy waterfall, you see me from a third eye point of view. Oasis in my arms, wonder why. You feel me, feel me, feel me, feel me. See me from a third point of view. Oasis in my arms, but I wonder why. You feel me right. You feel me right. Lay your grace on me. Let it wash. Summer dive, where you are. Feel me right. Feel me right. I lay your grace on me. Hallelujah, when she walks away. What am I doing, bro? Treat your body like a river and oh, see you coming at me like a wave. Touch me 12 ways, stars on the lake look like a million diamonds. Oh, let it wash all over me. See you coming. Ooh, ooh, ooh. Touch me 12 ways, stars on the lake look like a million diamonds. Oh, let it wash all over me. Oh, 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 yeah, yeah, yeah. Whoa, 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 whoa. Tenth waterfall, you see me from a third point of view. Oasis in my arms, I wonder why. You feel me, feel me, feel me, feel me, feel me, feel me. Ooh, ooh. Mm-hmm. Na 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 Fit me, rich. Fit me, right. I lay your grace on me. Hallelujah, amazing. When she walks away, that's my baby. Treat your body like a river and treat your body like a river and see you coming at me like a wave. Touch me 12 ways. Oh shoot! I see. This is this. Touch me 12 ways. Stars on the lake look like a million diamonds. Let it wash all over me. Gamma Hydra. So 154. Wash all over me. Ooh, doo, doo. Ooh, doo, doo. Ooh, doo, doo. Yeah, da, mm. Yeah, da, da, da. Mm. Da, da, da. Yeah, da, ooh, doo, doo. Do 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 do. Do 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 do. Do 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 do. Treat your body like a rose. See you coming at me like a wave. Touch me to the waist. Oh, wait, hold on. See you coming at me like a wave. Touch me to the waist. Stars on my leg look like a million diamonds. Let it wash all over me. See you coming at me like a wave. Touch me to the waist. Stars on my leg.
In this video, we'll be discussing how to convert carboxylic acids into their derivatives, as well as do a general review of a lot of carbonyl chemistry. Most carboxylic acid derivatives can be generated directly from the carboxylic acid. Acid halides are one of the derivatives that can only be generated from the acid itself. It cannot be generated from another carboxylic acid derivative, because acid halide is the most reactive of all of them. So in order to do this reaction, we'll treat the carboxylic acid with either a Cl2 cyanyl chloride or PCl3, if we want to make the acid chloride, or PBr33 if we want to make acid bromide. Acid anhydrides, as the name suggests, are two carboxylic acids that have been condensed and had water removed. So anhydrous means without water, so we usually heat these reactions up. We remove water as it's being formed, and by a naudable principle, we can favor the formation of the anhydride. Esters are formed from the carboxylic acid.
Let it wash all over. You see from the start, I wanted you. Oasis in my arms. Oasis. Du-du-du, du-du-du-du, du-du-du, ba-ba-ba-ba, ba-da-da, feel me, da-da-da, tenth waterfall. You see me from a third point of view.
And whichever alcohol we want to attach by treating under acid catalyzed conditions. And the final derivative of the carboxylic acid is called the amide. And these things cannot be made from carboxylic acid directly, because the carboxylic acid is acidic. The nucleophile we would need to make an amide would be an amine.
Halides, halogens, what's that, the 17th group? That makes sense. Anhydride. Left waterfall. You see me from a third point of view. Oasis in my arms. I wonder why. You feel me right. You feel me right. Making your erase on me. Hallelujah, you amaze. And she walks away. That's my baby. Amide is the one with 2. Amide is, it's the carbonyl thing. Treat your body, amine, amide. See you coming at me like touch me to a waist, stars on the lake look like $1,000,000. $1,000,000. They were showing me.
And what we see instead is a proton transfer between the acidic carboxylic acid and the basic amino group. So if I want to make an amide, I have to first convert the carboxylic acid into one of these 3 derivatives and treat one of these things with the amino group to make the amide. Now, when we think about carbonyl chemistry in general, I want to ask some big picture kinds of questions here. And the first is, how do we know what kind of nucleophilic reaction is going to apply if I'm looking at a given starting material? How do you know what happens when the MCAT throws some starting molecules at you? Well, the first thing you should do is find the carbon-oxygen pi bond. If we're going to do a nucleophilic addition, it's always going to happen because that carbon of the carbonyl is electrophilic, either because of a resonance justification or because of polarity. It will be electron deficient. So the next thing we'll be looking for is, what kind of electrophile do I actually have? If the electrophile is not that great, can we still do the nucleophilic addition? And the answer is yes, as long as the nucleophile is pretty good. And if the nucleophile is not that great, if the nucleophile is weak, then how do we make the reaction go instead? Well, there's 2 different things that we can: justification or because of polarity. It will be electron deficient. So the next thing we'll be looking for is, what kind of electrophile do I actually have? If the electrophile is not that great, can we still do the nucleophilic addition? And the answer is yes, as long as the nucleophile is pretty good. And if the nucleophile is not that great, if the nucleophile is weak, then how do we make the reaction go instead? Well, there's 2 different things that we can do. We can either make the electrophile a better electrophile, and usually we do that under acid-catalyzed conditions. Adding a proton onto the oxygen of the carbonyl gives it a positive charge, and therefore that carbon is more electrophilic. The other thing that we can do is we can make the nucleophile better. And usually we do that by deprotonating the nucleophile. So if I wanted my aldehyde or my ketone to be the nucleophile itself, I could make this into a better nucleophile by deprotonating alpha here to make an inaudible. Now, the other thing that might happen in these nucleophilic addition reactions is sometimes we see elimination happens after addition. So does that happen always? Well, only if I've got a good leaving group, so something electronegative next door to the carbon of the carbonyl. And if I don't have a leaving group, then what we're going to do instead is we're going to take that 0-, and we're going to protonate it via some acid workup steps. We will make an alcohol as the product instead. So when you think about all of carbonyl chemistry, there's really only 4 different kinds of things that could happen in their reactions. We're either going to do a nucleophilic addition, and sometimes be able to do an elimination. And if we need to activate our electrophile, we can protonate. If we want to activate our nucleophile, we can deprotonate. And then at the end of the reaction, if we had a good nucleophile to start with, and the nuclear condition happens first, then we'll protonate at the end to make an alcohol as we just described here. So if you think about this, we can review a couple of different kinds of reactions by just thinking about these 4 different steps. So if I were to protonate, meaning I don't have a really good nucleophile, so I'm going to activate my electrophile, then I let the nucleophilic addition occur, and then I deprotonate. Well, then that could be something like making an acetyl. Another option could be deprotonation first, meaning I don't have a great nucleophile, and I want to make it a better one. We get the nucleophilic addition to occur, and then we protonate the alkoxide at the end. That might be something like an aldol reaction. Another possibility might be to do a nucleophilic addition, and then a protonation, which means we already have a good nucleophile present. And then we're just going to protonate at the end, which means we don't have a good leaving group. So that might be something like hydride reduction, or maybe a Grignard reaction to make an alcohol. Finally, I could have all 4 of these things happen, so if I do protonation at the beginning, that means I don't have a great nucleophile. I'm going to activate my electrophile. I will allow the addition to occur, and then an elimination, and then we'll deprotonate at the end. So this looks like acid-catalyzed conditions to make some sort of carboxylic acid derivatives, most likely an ester. So you can see that lots of different types of reactions, making lots of different types of products, are all done under the same combination of 2 to 4 of these possible steps. So when you're trying to think about predicting products for carbonyl reactions on the end cap, don't worry too much about memorizing lots of details. The point of this slide was not to say memorize which combination of all these things is going to give you which compound out here. The point is to say all carbonyl reactions are going to have very common, very familiar types of steps in them. And in order to think through how the reaction might possibly occur, or a reaction that maybe you've never seen before, that you might have to deduce what's going to happen here, you should look to see whether you've got a good nucleophile, a good electrophile, whether you've got the potential of a leaving group in order to be able to predict what might happen. So to summarize the video, we saw that most
Let it wash all over me. Waterfall, see from the birds. Where's Waterfall, see me from the third point of view. Oasis in my arms, my window up. You feel me, feel me, you feel me, feel me. And you feel me. Lay your grace on me. Hallelujah, amaze me. And she was a woman. Oh my gosh, how many pop-ups?
Here's a dot structure for propane dioic acid, or malonic acid, and if you heat it up, it's going to undergo a decarboxylation reaction. So if we show free rotation about this bond, right, it's a sigma bond, so we can show a different conformation. Let me go ahead and draw in this carboxylic acid on the left, and then we were going to have a carboxylic acid on the right, too. This time the carbonyl is going to be going to the right, let me go ahead and put in those electrons, and the OH will be going to the left. So there we have it. All right, so in this mechanism, we're actually going to form a bond between this oxygen and this proton, and it's a cyclic mechanism. So if these electrons in here move into here, that's going to push these electrons into here, and then these electrons are going to form the bond between the oxygen and the hydrogen. So let's go ahead and show the result of our cyclic mechanism. Right, we'd have a carbon bonded to an oxygen, right, bonded to hydrogen, and then we have an OH over here, and then we'd have a double bond between this carbon and another carbon. On the right, we would actually form CO2. So let me go ahead and put in lone pairs of electrons on that oxygen, right? So we can see that we would form our carbon dioxide molecule here. So let me go ahead and draw those in. And let's follow some of those electrons, right? So the electrons in magenta right in here are going to move in, right, to form this bond, right, to form our double bond for CO2. And then these electrons in here in blue, so between this carbon and this carbon, right, are going to move over here to form this double bond, right, between this carbon and then there's a carbon right here. And then there's also two hydrogens bonded to this carbon. Let me go ahead and draw those in so we can see it a little bit better. And then finally, let's make these electrons in here red. So these electrons are the ones that are going to form this bond between the oxygen and the hydrogen. So we formed our CO2, and we've also formed an acid enol. Right, so this right here is called an acid enol, and we saw in earlier videos how the enol is in equilibrium with the keto form, right, with keto-enol tautomerization. And so this is actually the enol form of acetic acid, and so that's actually going to be our product. So let me go ahead and draw acetic acid up here. And here we have the OH on the left side, and then we would have a carbon over here with 3 hydrogens bonded to it, right? So this would be, if we're thinking about it, the keto type form, right? So the difference between the enol and the keto form are the movement of one proton, right? So there's a proton here in the oxygen, and here it's one of these in the carbon, and then the double bond. Here we have the double bond between the two carbons, and here we've moved the double bond between the carbon and the oxygen. So once again, we've seen how to do that in earlier videos. And then we also produce CO2, so carbon dioxide as the other product for this reaction. So the key to a decarboxylation reaction is having a carbonyl beta to a carboxylic acid. So for example, here's our carboxylic acid, and we know the carbon next to a carboxylic acid is the alpha carbon, and the carbon next to that is the beta carbon. And we saw how this carbonyl was necessary in the mechanism. And so the fact that there's an
Waterfall, you see me from afar. Waterfall, you see me from afar. On you, always just my arms. Treat your body like a river and see you coming at me like a wave. Touch me to a waist, stars on the look like a million diamonds. Let it wash all over me. Dehydration, followed by dehydration. Let it wash all over.
An OH here isn't really necessary. And what we really need is a carbonyl that's beta to our carboxylic acid in order for a decarboxylation reaction to occur. So let's look at another example, right, where we don't have a dioic acid anymore, right? We have a carboxylic acid on the right.
Let it wash all over. See you coming at me like a wave. Touch me away, stars on the lake look like a million diamonds. Wash all over me. See, let it wash over me. See you coming at me like a wave. Touch me away, stars on the lake look like a million diamonds. Wash all over me. I wanna fall. You see me from a third eye point of view. Oasis in my arms, I wonder why. You feel me, feel me, feel me, feel me, feel me. Oh, doo doo doo.
And then over here on the left, we have a ketone. But again, the key point is, here's the alpha carbon and here's the beta carbon. We have a carbonyl that's beta to our carboxylic acid, and so therefore a decarboxylation reaction can take place. So if we heat up this molecule, once again thinking about the mechanism, rotating about that sigma bond, right, let's go ahead and redraw this. Right, so we have our benzene ring, and then we have our carbonyl right here, and then we would have, once again, our carbonyl going off to the right this time, and then our OH over here on the left. So thinking about our mechanism, once again, we know...
See me from a third point of view. Oasis in my arms, I wonder why. You feel me, feel me, feel me, feel me, feel me. Feel me, feel me, feel me. Leo. Oh, this goes here. Okay, I see. You amaze me when she walks away. That's my baby. Treat your body like a river run. See you coming at me like a wave. Touch me away, stars on the lake look like a million diamonds. Oh, let it wash all over me. See you coming at me like a wave. Wash all over me. Not a waterfall. You won't see me from a third eye point of view. Look oasis in my arms, and I wonder why.
It's a cyclic mechanism. We know this oxygen is going to bond to this proton, and so these electrons are going to move into here, and these electrons move into here, and these electrons move into here. So that's our...
They see me from a third eye point of view. Oasis in my arms. Let it wash all over me. Treat your body like a river. See you coming at me like a wave. Touch me away, stars on the lake look like a million diamonds. Wash all over me. Treat your body like a river run. See you coming at me like a wave. Touch me away, stars on the lake look like a million diamonds. 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 million diamonds, let it wash all over me. Yeah. Pooch, let it wash all over me. Let it wash all over me. 10-time waterfall. You see me from a third eye. Oasis in my arms. Let it wash, let it wash, let it wash, let it wash all. Mm.
Our cyclic mechanism, when we draw what happens, right, moving all those electrons around. We have our benzene ring. We would have it bonded to an oxygen. This oxygen was bonded to this proton now, and then we have a double bond right in here. And then we also form CO2. So once again, let's run.
O2.
Let's run through those electrons and try to follow some of those electrons here. So let me draw on these lone pairs of electrons on our oxygens, right? So we can see where the CO2 comes from. So once again, these electrons in here in magenta, right, are going to move in here to form the double bond on CO2. At the same time, these electrons in here are going to move into here to form this double bond. And then finally, these electrons in here are going to move out to form the bond between the oxygen and the hydrogen. So we've made our CO2. So the oxygen, carbon, oxygen, right, comes from this oxygen, carbon, oxygen right here on the molecule on the left. So hopefully that's a little bit easier to see now. And once again, we have an enol, right? So we form our CO2. We also create our enol. And so we can think about keto-enol tautomerization for our product, right? So the enol is going to be in equilibrium with the keto form. So let's go ahead and draw the keto form, which we know is moving one proton and moving the double bond. So we move the double bond between the carbon and the oxygen, and we move that proton to this carbon right here. So this carbon right here picks up a proton. So down here, that carbon had two hydrogens, right? And it doesn't have to be this one right here, but we are going to add a hydrogen to that carbon, and that gives us our final product, our ketone. So this decarboxylation reaction produces a ketone. And once again, it doesn't really matter what this R group is here, right? Here we have a benzene. Are going to add a hydrogen right here, picks up a proton. So down here, that carbon had two hydrogens, right? And it doesn't have to be this one right here, but we are going to add a hydrogen to that carbon, and that gives us our final product, our ketone. So this decarboxylation reaction produces a ketone. And once again, it doesn't really matter what this R group is here, right? Here we have a benzene ring instead of the OH in the previous example. And then, of course, we're also going to make CO2. So decarboxylation reactions are going to be important in future videos where we're synthesizing some complicated molecules. And so here is this is the cyclic mechanism for it. Previous example. And then, of course, we're also going to make CO2. So
Yeah. Let it wash, let it wash on. Treat your body like a river. Dig like a wave. See them. Shalom.
In this video, we'll be discussing the aldol reaction and various aspects of enolates. Now, the aldol condensation is an example of a nucleophilic addition reaction, where I get an aldehyde or a ketone to react with itself. And we do that by treating the carbonyl compound under basic conditions, such that we can deprotonate the acidic alpha hydrogen. And when we do that, we make a nucleophilic enolate molecule. Now, not all of the alpha hydrogens can be deprotonated. However, because the hydroxide is not a good enough base, so there is a really large percentage of the original carbonyl compound still in solution. So now, in this same container, itself, and addition reaction, where I get an aldehyde or a ketone to react with itself. And we do that by treating the carbonyl compound under basic conditions, such that we can deprotonate the acidic alpha hydrogen. And when we do that, we make a nucleophilic enolate molecule. Now, not all of the alpha hydrogens can be deprotonated. However, because the hydroxide is not a good enough base, so there is a really large percentage of the original carbonyl compound still in solution. So now, in this same container, we have the molecule in its nucleophilic form and in its electrophilic form. So they can react with themselves, so the nucleophile will do an attack on the electron-deficient carbonyl carbon. We'll push some pi electrons out onto the oxygen, and we'll make this new tetrahedral intermediate. And the new bond is this bond right here, that I've highlighted between the alpha carbon of the enolate and the carbonyl carbon of the electrophile. Now, under acidic conditions, we can just protonate that alkoxide and get the final product here, which would be a beta-hydroxycarbonyl. So remember, if the alpha position is one carbon away from the carbonyl then that means that the beta carbon is one more carbon over. Now if I continue to heat this compound up, I can get that OH group and the remaining alpha hydrogen to eliminate and lose a molecule of water. And we end up then with an alpha, beta unsaturated compound. Now it's not your job on the MCAT to know whether you get the beta hydroxy compound or the alpha beta unsaturated one. But it is your job to recognize that both of them are fair game products for the aldol reaction. You should also be able to, if you see this pairing of functional groups, be able to reverse engineer this compound and identify what the starting materials were for the aldol reaction. Now this reaction is shown as what we call a self-aldol reaction, because the molecule reacted with itself. We'll push some pi electrons, and when we do that, we make a nucleophilic analate molecule. Now, not all of the alpha hydrogens can be deprotonated. However, because the hydroxide is not a good enough base, so there is a really large percentage of the original carbonyl compound still in solution. So now, in this same container, we have the molecule in its nucleophilic. Do that by treating the carbonyl compound under addition reaction, where I get an aldehyde, various aspects of enolates. Now the aldol condensation is an example of a nucleophilic addition reaction, where I get an aldehyde or a ketone to react with itself. And we do that by treating the carbonyl compound under basic conditions, such that we can deprotonate the acidic alpha hydrogen. And when we do that, we make a nucleophilic analate molecule. Compound. Now it's not your job on the MCAT to know whether you get the beta hydroxy compound or the alpha beta unsaturated one. But it is your job to recognize that both of them are fair game products for the aldol reaction. You should also be able to, if you see this pairing of functional groups, be able to reverse engineer this compound and identify what the starting materials were for the aldol reaction. Now this reaction
always gonna die where you are. Fit me right. Fit me right. I need a star. Your face is like a full universe.
reaction is shown as what we call a self-aldol reaction, because the molecule reacted with itself. And we only get one product or one possible way that enolate and the electrophile can react with each other. But if we were to use a ketone and an aldehyde, or two different ketones, or even have a self-aldol condensation with an asymmetrical ketone, we could get more than one product to form. And in those cases, that would be called a mixed aldol reaction. So when we're choosing what aldehyde or what ketone we want to use for the aldol reaction, we have to plan a little bit to make sure that we try to minimize any byproducts that we don't want. So let's take a little bit of a closer look at some other aspects of enolate ions. So first of all, you should be able to look at any aldehyde or ketone and identify how many different enolates can I form from that particular compound. So, if we look at an aldehyde like this, again, we're looking for really how many different kinds of acidic hydrogens or alpha hydrogens do I have in the compound. So the first compound indicated has one alpha carbon because it's and aldehyde. But notice that there's already 4 bonds to this carbon, so there is no hydrogen here. And this hydrogen, directly bonded to the carbon of the carbonyl, is not acidic because it's not adjacent to the pi bond. So I don't have any acidic hydrogens here. And so I'm going to have 0 enolates that I can form. So this molecule would be a great choice in an aldol reaction for the electrophile because I can't make a nucleophile out of it. Similarly, the compound directly to its right is in the same situation. So not acidic because the aldehyde hydrogen. And this is a quaternary carbon, so again, I don't have any alpha hydrogens I can deprotonate. Now the two ketones below are a different situation. The compound on the left has one type of acidic hydrogen at this position, and a second type of acidic hydrogen at this position, because this compound is asymmetrical. So I can make a total of two different enolates with this starting material. And if I look at the last molecule, it's the same situation. I've got hydrogen between the carbonyls that are different than the hydrogen to the left of the left carbonyl. So I can make two different kinds of enolates from this compound as well. So let's take a look at these ketones now in a little bit more detail. The first thing I want to consider is, if I treated this compound with one equivalent of base, which of those two hydrogens would I deprotonate first? Meaning which one is the stronger acid? Now to identify a strong acid, we want to think about the stability of the conjugate base. So if I were to take off the blue hydrogen, I'd get an enolate that looks like this. And I could draw a resonance structure to help to stabilize that looks like this. So technically, upon deprotonation, I would have the charge at this position. And again, I can push the electrons to show how I get the first enolate that's drawn. So I've got two different resonance structures if I pull off the blue hydrogen. If I pull off the red hydrogen, I'm going to get a negative charge at this carbon right here. But again, I can resonance stabilize that out onto one of the oxygens. So in this way, or I could push these electrons all the way over to the other oxygen as well. And remember, oxygen being more electronegative helps to stabilize the charge even more. So I can get a total of 3 resonance structures now. If I were to push the electrons to this carbon, I'd get my third resonance structure, so by removing the red hydrogen between 2 carbonyls, I get 3 resonance structures here, whereas up here I only get 2. So the more resonance structures I can draw, the more stable the conjugate base, and therefore the more acidic the hydrogen. So this is a really big difference in terms of stability, and I would expect to deprotonate the hydrogen between the carbonyls exclusively, with one equivalent of base before I even begin to deprotonate here. Now the other thing that I want to talk about in terms of enolates is to look at that first asymmetric ketone. And again, consider what happens if I take off the blue hydrogen or the red one. So the question on this slide is, which of these is more stable? The enolate on the left or the enolate on the right? So you might remember that the more substituted a carbon-carbon double bond is. So in this case, I've got 2 carbon groups attached, as opposed to just this one carbon group attached. Makes it more stable. So the enolate on the right is more stable because it's more substituted. And because it's more stable, we call it the thermodynamic enolate. And if I want to favor the formation of the thermodynamic enolate, I can do that by using a particular set of reaction conditions, which happens to be a small base and at least room temperature, or maybe even elevated temperatures. On the other hand, if I wanted to favor the formation of the enolate on the left, then I've got to do that under a set of conditions that makes it easier to pull this hydrogen off than it is this one. Now the big difference between these 2 hydrogens is their substitution level. The one on the left is a primary hydrogen because it's attached to a primary carbon, and the one on the right is a secondary hydrogen because it's attached to a secondary carbon. So that means that this one is less hindered, so I can favor its deprotonation if I use a sterically hindered base. And in doing that, I make it form faster, so removing the blue hydrogen gives me a less substituted and less stable enolate. However, it forms faster if I use a really bulky base and low reaction conditions, low temperature conditions. And this thing, because it forms faster, is referred to as the kinetic enolate. So if I'm going to use an asymmetrical ketone in an aldol reaction, and I want to deprotonate on one side or the other, I can control that by an appropriate choice of base size and reaction temperature. So to summarize this video, we looked at the aldol reaction and how I can have both a nucleophilic form and an electrophilic form of an aldehyde or a ketone to react with itself. I see that I can make two different kinds of products, either a beta-hydroxycarbonyl or an alpha-beta unsaturated one. And then we looked at various aspects of enolates, including, and most importantly, the difference between the kinetic enolate and the thermodynamic enolate, and how I can form one over the other by adjusting either the base size or both the base size and the temperature conditions. Most importantly, the difference between the I make it form faster, so removing the blue hydrogen gives me a less substituted and less stable enolate. However, it forms faster if I use a really bulky base and low reaction conditions, low temperature hydroxycarbonyl, and the
Sending this to all my undergrad friends.
Now I'm wondering what's with her. Something's on her mind. As I reach out for her fingers, I nervously smile. I see that she's about to end it. A tear falls from her eyes. Either way, just get it over with. Maybe I destroyed your trust, or what we've built's not enough. Either way, just get it over with. Maybe all of my past lies explains the coldness in your eyes. Either way, just get it over with, please. Let me go. Let me go. Let me go. And if you can't hold on to love, let me go. It's like, now that you're finished, it's like, where do I start? I'm questioning my father above. It's like your spirit's on a labor strike in the heart, cause you don't want to work towards love. And I know sometimes I got a rough edge, and this ain't no picnic, no club med, no Beavis, and sometimes we gon' butt heads, but isn't that why we gotta work? I mean, look at me, you're not even looking at me. No, get it over with, I'm dangling, just cut the rope. You got the balls to write the letter, seal this envelope. Go ahead, get it over with, finish the job, go ahead. Maybe I destroyed your trust, or what we've built's not enough. Either way, just get it over with. Maybe all of my past lies explains the coldness in your eyes. Either way, just get it over with, please. Let me go. Let me go. Let me go. And if you can't hold on to love, let me go. Oh, oh, let me go. 'Cause I can't take it anymore.
Mm, mm, mm. Yeah. No wonder, I wonder what was with her. Mine. Either way, either way. Either way, just get it on. Mm, 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 mm. Maybe your life explains the coldness in your eyes. I mean, I'm cleaved, carbonate. 5. Either way, just get it over with. No, carbonate 1, 2, 3, carbonate. Something's on her mind. And I see, and I'm sweet to her with her. Done another mind. I see she's about to end. A teardrop falls her eye. A tear comes her eye. Either way, just get it over with. Yeah. Maybe all the friends left. Make no plans. Either way, just get it over with. Maybe all of my past lives explains the coldness in your eyes. Either way, just get it over with. Let me go. Mm. Mm. Let me go. Yada do. Let me go. Mm. Mm. Let me go. Seas ended. Teardrop falls from her eye. Either way, just get over me. I promise. Either, just get it over.
In this video, we'll be discussing enzyme inhibition. Let's start by reviewing our V versus S graph. This is a graph for an uninhibited reaction. On the vertical axis, we've got V, the rate of product formation, and on the horizontal axis, we have the substrate concentration. And we see this curve where it kind of levels off at some point. The point where the curve levels off is called Vmax for the reaction. Inhibitors bind at the active site. Vmax stays the same in the world. And what he decides to do is create himself a little carnival that he's going to call Joe Schmo's World of Fun. And it's basically like Carnival Midway game. You have a long box. You get all 10 balls box. Not Schmo, a beer. Pretty soon you've got like 100 in your big active site and not inhibitor, and you'll hit your Vmax. Joe becomes wise to your tampering with this balls in the box game and decides what he's going to have to do is make the game even harder. So he installs a switch on the side of the box. And the switch will control a little net. So if he flips the switch, a net appears at the hole that's in the bottom of the box. So a ball can kind of go through but not all the way through. It sort of gets held there with that net. So this is also going to reduce the rate at which balls go through the hole. But you're never going to be able to hit your Vmax under these conditions. You're never going to get your 10 balls through in a minute. His plan is just to stand there and flip the switch. On, off, on, off, on, off. And this is like our second type of inhibitor called a non-competitive inhibitor. Now, non-competitive inhibitors do not bind at the active site. They bind at the allosteric sites to the empty enzyme. The allosteric site at the enzyme by itself. So CAM is going to, if you reduce your functional amount of enzyme, you reduce your Vmax. Let's put this one on the graph. Non-competitive inhibitors we're going to put here. These guys are going to level off at a lower Vmax. They're going to have a reduced Vmax. So here is our Vmax for our non-competitive inhibitor. Is also going to go down because Vmax substrate. You could put as much does not affect but affects the when they bind to the enzyme alone, they might change the active site. So now it's harder for the substrate to bind, or the substrate can't bind at all. In any case, they're all going to reduce Vmax because they're allosteric inhibitors. You could put as much substrate as you wanted in there, and it's not going to change the effect of the inhibitor because the inhibitor is binding somewhere else. So the effect on Vmax is going to go down, and we can't really predict to the effect on Km. If the mixed inhibitor binds to the inhibitor, if it wants you to think about, summarize what we talked about in this video. We reviewed the V versus S graph, and we looked at how different types of inhibitors, competitive, non-competitive, uncompetitive, and mixed inhibitors, could affect that V versus S graph.
Well, I gotta go. I don't know that use of time. 2 hours. I could have done more. Annoying. Okay, I'll see you later. Maybe tonight? No, I'll be too tired. We'll see.